a fundamental concept in engineering physics. This presentation will cover both theoretical and experimental validations, providing a comprehensive understanding for undergraduate students and instructors. First of all, what is bending of beams? What is bending moment? And how do internal forces create a moment that cause a beam to bend? So these images are shown in the cantilevers examples bending beams. Introduction to cantilever beams. Cantilever beams are ubiquitous in modern engineering, serving diverse functions from structural supports to precise measurement devices. Definitions of cantilever like as a beam supported to only one end, with the other end free to move or deflect under load. And the real world relevance of the cantilever like as bridges and balconies, aircraft wings, micro electromechanical systems, sensor applications. Basic of this beam concept, understanding the internal forces within a beam is crucial for predicting its behavior under external loads, like as the images are shown in the basic of beam theory. In this beam theory, defined as a two different methodologies like a shear force, the internal force acting perpendicular to the beam's axis, tending to cause one section to slide past another. Bending moment, the internal moment acting about the beam's cross section, causing it to bend. It is the algebraic sum of moments of all external forces to one side of the section. Bending moment in a cantilever. For a cantilever beam subjected to a point load at its free end, the bending moment varies linearly along with the length. So equation of bending moment m is equal to minus p into x, where p is equal to applied point and x is equal to distance from the free end. In the negative sign indicates sagging moment, compression at the top, tension at the bottom, like as the that's in image as shown in the figure. Deflection equation of cantilever. The deflection of cantilever beam is critical parameter indicating its stiffness and structural integrity. Maximum deflection delta it's equal to PL cube divided by 3EI. P is equal to applied point load. L is equal to length of the cantilever. E is equal to modulus of elasticity. I is the moment of inertia. In this formula highlights the significant impact of beam, length and material properties on deflection. Stress distribution in cantilever beam. Bending stress like as sigma it's equal to my divided by I, where m is equal to bending moment of the session, y is the distance from the neutral axis, I is the moment of inertia. In stress is zero at the neutral axis and maximum at the top and bottom fibers. In the experimental setup of cantilever, to validate theoretical prediction, a carefully arranged experimental setup is essential for accurate measurements. Materials like as cantilever beam, like as examples of steels, aluminum, wooden materials, any kind of one. And weights or load hanger, like as in this image shown in the side. Measurement method fixed support clamp, dial gauge for deflection measurement, and measuring tape or calipers for dimensions, length, breadth, and height. Experimental observations and results are shown in the graph, recording and analyzing the relations between applied load and measured deflection provides critical insights. In the key recorded trends like as linear relationship between load and deflection. Deflection increases proportionally with the increasing load. Data collected always allows for the calculation of experimental Young's modulus. In the small deviations from linearity indicated the onset of plastic deformation or experimental errors. And resultant discussions of this theory and experimental method in the graphical method shown as the comparative analysis reveals accuracy of theoretical and experimental values typically show close agreement for small deflection. The difference helps validate the foundational equations of beam theory. Factors of affecting deviations, measurement error, digital gauge level, and beam dimensions, non-ideal fixed support condition, material non-uniformity, initial imperfection in the beam. Thank you guys. Thank you very much.